Okay, so new chapter. We're going to look at systems of particles. A system of particles. Okay, this is a situation. We have an inertial reference frame N. Origin O is fixed in N. And I have many particles, P1 mass 1, P2 mass 2, etc. Pn mass n. Okay, these are the position vectors measured as with respect to the point O. So this is R1, R2, etc., Rn. So we have this system which is composed by all these masses here, M2 and N. Okay, and say that each resultant force acting on each particle is given by the vector R, 1, 2, 3, up to N. Okay. So if I give you something like this, what can you tell me about the particles? What is true for all of them?
They're going to act upon each other?
Maybe. They may or may not. So that's probably not something I can generalize, but more basic, more fundamental. This is an inertial reference frame, and you're looking at several particles that move around. They're not constrained. I'm not making any other assumptions other than I have a bunch of n particles that they move in 3D Euclidean space, and I'm looking at them from an inertial reference frame, and I know that the resultant forces are R, R1, 2, 3, etc. What can I say about them? Something very basic.
They have the same fixed point.
There's no fixed point. Well, they're all, well, yeah, I told you that the position is measured with respect to the origin of the coordinate system fixed to the reference frame, yeah, right? All the position vectors are measured from O, but I gave you that. Okay. What is true about these particles here? There's really nothing special other than what I gave you, but what I gave you should be enough to observe one thing that we're going to use to derive some results. Without that, we cannot really do anything today. We're doing this, right? We do kinetics. What did we say when we started doing kinetics? Where did we start from? Which is called? That's Newton's second law. So what is true about these particles here? What is valid for all of them? Not only that one, all of them. So the laws of mechanics, the three laws of Newton, actually apply here, because I am in an inertial reference frame, and so each one of these particles, unless is acted upon a force, will maintain its state of motion, will stay at rest or continue with the same velocity. That's the first one. Then F equal ma in n. Remember, that's not a generic acceleration. Acceleration is not by itself defined unless you tell me in which reference frame is computed. And so F equal ma in an inertial reference frame. It's valid for each one of them. And for every action, there's going to be a reaction. So those three can be used in this setup. Okay. That's important. Otherwise, I cannot do anything. Okay, so let's see what I call these forces here. I call them R. Yeah, I think I call them R. Yeah. So if that's true, the one thing that I care about particularly is that Ri is equal to MIAI in n, with I goes from 1 to n, right? And say that I decide, as we have done already for energy in particular, I think we've done it, say that Ri can be split into the resultant of all external forces so this is the resultant of I call them external, well no, we haven't actually done it before, external forces acting on Pi, on the particle P of mass Mi, plus, what do I have here? I need to define this. So let's define the following force, Fij. This is the force on I from J. So as someone mentioned before, they can exchange some forces somehow. I didn't make any particular assumption, so they can in principle. And so before I complete that equation there, let's make another assumption here. So everything we build is based on some assumptions. Assumption is that, well, definitely this needs to be valid, right? Action, reaction. So if J is exerting a certain force on I, well then J sees the same force, opposite force on itself exerted by I. And I'm also going to assume, so this is Newton's third law, right? This was the second. Okay. And I'm also going to add that if this is particle I, or Pi, whatever you want to call it, J, I'm adding an additional assumption here that if this is Fij, and this is of course minus F, I'm sorry, this is wrong. No, this is right. Okay, yeah. This is minus Fij, right? I am going to assume that not only they are equal and opposite, they're also on the same line of action, which I'm not going to use today. We'll use it next time with definition of angular momentum. But this is, what is this called? We gave it a name. By itself, Newton's third law doesn't really tell me that the forces need to be on the same line of action. They just need to be equal and opposite, action, reaction. This is the strong form, right? Now this is true for most of interactions that we can have in nature. If you start going into electromagnetism, this is not true anymore. Particles can actually exchange equal and opposite forces that don't lie on the same line of action. But we're not going to do that. So we assume that this is valid. For mechanical systems, it is valid, unless you have electromagnetic forces. So we're going to assume strong form of this equation, of this law. Okay. Well then, what do I have here? If I'm looking at one particular particle here, and I want to write Newton's second law, here I have to have all the forces that act on that particle. And I decide to split them into the ones that come from outside, so they're not caused by any interaction with the other particles. And then, of course, here there will be all the, what we call the internal one, right? All the forces that I sees because the other particles are acting on it somehow. So this is going to be the summation over J that goes from 1 to n of Fij. Right? This is the resultant of, well, call them internal forces acting on I, on PI. Okay. Making sense here? So these are the forces that appear because you are in a system of particles, because there are the other particles around you. Now, with these assumptions in mind, what I'm going to do is, well, everything is dropping. I'm going to start from this and do a summation of all these equations over the system. I can do that, right? I have an equation, I can do whatever I want. See if I get anywhere. So summation over I now, 1 to n of fi plus, now I have here summation over I, 1 to n, and then summation over j, 1 to n of fij is equal to summation over I, 1 to n mi, the acceleration of the particles in the inertial reference frame. Any problems up to this point? Pretty simple, right? What is this? What do you think? Given the assumptions I've made, you're basically adding up, is 0, right? You're adding up all these forces that the particles exchange with each other, all of them. So for each one of them, there is an equal and opposite, so they go in pairs, and this will be always 0. So if you sum up all the internal forces that exchange with each other, you're going to get 0. So, okay, I don't think we need this anymore. I get the summation of fi is equal to summation of mi ai in n. 1n, it should be obvious that I'm summing over the masses. Okay. So at this point I come up with another definition, which is R bar. It's the summation of mi ri over summation of the masses, and this is called the position. Remember, these are things that I define, of the center of mass. So from now on, the bar is going to indicate properties that have to do with the center of mass. That's the definition. It's a weighted average of all the positions of the particles where the weights are the masses. Now, of course, you probably know where I'm going with this, but let's do it in a formal way. What is the velocity in n of that point, this center of mass point? I'm telling you it's going to be this, but you tell me why. Why can I do this?
Differentiate mass.
Masses are constant. The operator that takes the rate of change is a linear operator, so I can do this, right? I can say this. And the same for the acceleration. Acceleration of the point center of mass is going to be equal to the weighted average of all the accelerations of these single point masses. Of course, all these sums are over I. I'm just getting lazy and I don't write it anymore. Okay, now, as we all know, this center of mass point, it's a definition, it's a fictitious point, right? Doesn't really exist. It doesn't have to exist per se. If I have two masses, m1 and m2, and that's my system of particles, that's it. That's a perfectly fine system. This is not a connection. This is just the line connecting the two. Center of mass can be a point right here where there is no actual mass. It's a definition. You may fall into a point where there is a mass or not. If you have a donut and the mass is uniformly distributed here, the center of mass is right in the center. There is nothing here. There is nothing you can eat from the center. But there is a lot you can eat from around it. So that's just a definition. Okay, how do I use that definition now? Let's define again. Let's say that m is the total mass of the system. Okay. It looks like if I take this last expression here and I multiply both sides by the summation of mi, which is m, big M if you want, well, this sounds familiar, right? It's up here. So with these two ingredients, the definition of position of center of mass and the derivation of its acceleration, and the fact that we are in an inertial reference frame, Newton's laws are valid and we are enforcing them. This is how I got here. You can say that the summation of all these Fi's, which remember are the external forces, is equal to, what is it equal to? Big M, I'm not calling it big M, but just M without i's, which is the summation of all the masses, A bar in N. Correct? And so one more step, if we want, is just calling F, the summation of all external forces, just call it F, big F, or F we know no indexes at this point, resultant of all external forces on the system. Okay, fine. So one more combination of definitions. I write my final equation F equal ma bar in N, where this is the summation of all the external forces that act on your system of particles. This is the total mass of the system, and this is the acceleration of the center of mass. Now, these look like a lot like what? I actually forced that to look like that, but once I get to this expression, it looks like what?
The second row.
It looks like Newton's second law. Is that a law, though? I'm asking you. Can you call that Newton's second law? Keep it simple in your mind. A law is something that I walk into the classroom and I tell you, this is it. Accept it or just go and live on another planet, because on this planet this is how things work for the most part. That's a law. Someone observed it for long enough and came up with a law, and no one has proved that guy wrong, so that's a law. We accept it. To get to that, I had to erase a couple of boards. That's not a law, that's a derivation. I used Newton's second law applied on each single particle to get there. Not only that, also the third law. But that is a derivation, so if someone tells you that this is Newton's second law, you can tell them you don't know what you're talking about, because, well, first of all, Newton's second law applies to a particle of mass m. This point, center of mass, may not even have any mass. It's a fictitious point that I just made up. It's the center of the donut. There is no mass there. You can't say that you're applying second law of Newton to an empty point in space that has no mass. There is no kinetics for a point with no mass. If there is no mass, there is no kinetics. You throw away everything we've done when we started kinetics. So this is a derived result. It's telling me simply that with this definition of a point called center of mass, this guy here, which is something I make up, well, the system of particles will move in time, and the center of mass will move as if it were a point where all mass is concentrated, big M, or M, summation of all the masses. And that point is moving under the action of only the external forces. It's a useful result that we can apply to problems. But again, the center of mass is not a real point, may not even have a mass, may not even be on the body that you're looking at. Again, donut. That point is not on the donut. There is no mass at all. But it's a very useful result. So when you're looking at a system of particles and you're able to define the center of mass and compute its acceleration, and you know the masses that are involved, you can just ignore everything that happens inside the system. You just care about what happens outside the system, and that is giving your F. Making sense? This should be something that is not new at all at this point. If you've taken any dynamics classes, really. Any questions? This was pretty straightforward, right? How do we use all this? Let's start solving some problems. And I'll do the classical inclined plane with a block on it and both they can move, just to see how these things are actually applied. Okay. So when we move to system of particles, until we do angular momentum, we really do this more or less the same things that we've done with particles. We start from kinematics, find accelerations, and then, as we'll see, we will deal with free body diagrams, and that's where the problems start, because you're going to have more than one. And you need to pick the ones that you really need to find the equations of motion. Do you need to pick the right ones? Okay, so we have ground here, which is inertial. So this is an example. A standard one. I give you standard examples because they are built to explain basic concepts. Doesn't make sense to create very complicated ones just to show off and confuse even myself. So what's the point? Okay, so this is a wedge or inclined plane, call it whatever you want. First object. It's a rigid object actually. And then I have a block that can move on it. This is supposed to be a square. So this is mass m1, this is mass m2, and I'm already kind of giving you coordinate systems here. Okay, there is no friction between the wedge and the ground, but there is friction here between the two objects. Viscous, doesn't matter. Why am I always giving you viscous friction, by the way? What do you think? We've done the other one as well. We've done Coulomb friction, right? In both cases, you have to find the V relative. But with the Coulomb friction, you also have to find the normal force. So it's probably a little more complicated. You actually can't ignore those normal forces that in many problems we say, hey, I can get a differential equation without caring about the normal force. You cannot do that with the other model for friction. So kind of being lazy here, but you can. You just can't ignore the equations that give you reactions in the case. Okay, I want, of course, the differential equation of motion here. Okay. And as always, before we start doing anything, we make a few comments. How many? So we'll do systems of particles here. And I'm going to abuse terminology and treat these two as particles because there is obviously no rotation. So these things are going to translate. The wedge can only go back and forth on the ground, and the block can only go up and down. Well, there's no way. Oh, there is gravity, of course. Sorry, forgot about that. It can only move on the slide here on the wedge, so I don't see any rotations. So even though this is, you know, figures that really make us think about rigid bodies, I can treat them as particles. Now, how many equations do you expect? Two equations of motion, right? Because one is going to give me the position of the wedge on the ground, and the position of the block on the wedge is completely independent, so I do need another variable there. So I'm actually giving you already the variables that you will need to use to find the differential equations, so that's a good guess. If I give you a problem like this and you already have x1 and x2, why would you tell me that you need 3 differential equations of motion? I mean, it's already there for you. Okay, I need 2. Good. So with a problem like this, the tendency is usually, geez, I have to solve all these things all together. This is a lot of stuff going on. This is moving here. There's friction here. What I'm telling you is you do one object at a time first. Then you treat it as a system of particles, as we'll see. But first you do one at a time. You do kinematics for each one of them, and then you put them together. You don't have to look at the problem and try to solve it all together at once. So we do as usual. There's nothing really fundamentally different here. We pick the reference frames, first of all. How many do you think I need? You, in principle, you just need one. There is no rotations here. So I can really just pick the ground. But I'm going to pick the wedge as well, just because it makes my life easier. And, you know, I kind of gave you already a coordinate system attached to the wedge there. So, but it's not required. You could do it with just one. So my recommendation in general as well when you face problems is don't fall short of on the reference frames that you define. You may define more and not ever use them. That's fine. It's better to define more and not needing them than being short. So as I was, you know, preparing examples and working out problems, I found out in many cases that I had too many. I didn't need them. I actually defined them and never used them. Who cares? That's fine. That is not a mistake. It's just being conservative. So G is the ground. And I'm going to say that, of course, the origin is when x1 is 0. I gave it to you. So Ex is, what do you want to do? Well, I can say along, what do you want to say? Along ground to the right. Ey, I can do it either way, along minus g, just pointing up, and Ez is Ex cross with Ey. So this is what I have. Let me do it down here. I have Ex, Ey, Ez. And then I told you I want to add another one, just because I think it's going to make things a little easier. So this is a reference frame, which is that triangle, the wedge. And so, yeah, that's a reference frame. The origin is when x2 is 0 in this case. So x1 gives you the position with respect to an observer fixed to the ground of the wedge, and x1, and x2 gives me the position of m2 with respect to the wedge itself. So this makes sense. The origin is fixed in the wedge reference frame. Little ex along how do we call that direction? Down the slope. Right? That's a defined direction. It's the direction of x2. And let's say that EZ is the same. And EY is going to be equal to EX, I'm sorry, EZ cross with EX, right? So if I do it that way, I have little ex pointing down this way. This is the angle beta, right? Which is a constant angle, by the way. It's a rigid body. I told you. I'm abusing it, treating it as a particle, but it's not changing shape or anything strange of that kind. So that's what I have, right? Okay. I have these two coordinate systems, reference frames and coordinate systems. Now, kinematics. Forget about the block. Let's do one piece at a time. Let's do the wedge. So I will have to find the accelerations of these two objects, of these two masses, of course, to be able to write F equal ma in g. And so we start from the position of the wedge first. What is that? x1ex. So without even thinking about it, the acceleration of the wedge in g is x1 double dot ex, right? Position of the block is, I want to say this is probably a good idea to write it as the position of the wedge plus the position of the block with respect to the wedge. So this is x1 ex plus x2 little ex. And I'm telling you that I don't have to think about this that hard, because AB in G is going to be x1 dot ex plus, I'm sorry, x2 double dot plus x2 double dot little ex. Do you agree with me? If you agree, why?
Well, because the angular velocity between those two are zero, so the transfer function is not necessary.
The transport theorem really doesn't do anything. Or another way that I think, to me, makes things clearer is saying that basically the two reference frames that I picked are both, the two coordinate systems, I'm sorry, that I picked are both fixed, except the center of the second one, which is not fixed, of course. But the bases that I picked are fixed in G. The direction little ex, little ey, and little ez does not change in G. That's why this is a redundant reference frame or an coordinate system, really. All I'm doing is taking the basis big Ex and big Ey and rotate it of an angle which is constant in time. So basically this is little X is not going to change in G. So it's just because it makes it more convenient for me. But as I told you, in principle, you don't need a second reference frame. But we use it. Okay. And I stop there for kinematics, really. I don't think I need to do anything else. So this was kinematics. Well, one thing that we could do is now compute the acceleration of the center of mass, since we're looking at a system of particles, but we'll do it later. Now, kinetics. What do we do when we start kinetics? First thing we do, free body diagrams, one at a time. Okay, so what are the forces acting on this wedge object here? Okay, M1G. Be careful now, you have different masses. Don't drop the right notation. What else? Normal force, there is no friction with the ground, but there is still some normal reaction here, N. Okay? I'm just putting them along the same line here, but if you want, I can move it. Maybe I should move it. Okay, mg is down here. I decide to draw N like this, fine, which is perpendicular to the, basically it's along EY, right? Because there is no friction. What else? The block is doing something. These things are touching each other. So what's happening here is there is a reaction component, which is the perpendicular to the wedge surface, right? And there is a force of friction. Fine. That's all I have for this guy. Now I do, so this was the wedge. Now I do the block. This is your block. What do I have? I start with the ones we know, right? M2G is there. There is gravity. So M2G. What else? Now, how would you, what would you do here? What do you suggest me to draw? You be careful with this, because then I'm going to do another free body diagram that is not going to make sense unless you do this right. And this is a conceptual mistake if you don't do this right. What do I draw here?
If it's in opposite direction of the wedge.
So if that's R, I have minus R. Now the sign does matter here. When I told you don't make up signs unless they're needed, well, here it's needed. Otherwise, you're telling Newton, who cares about your third law? I don't care about it. If this is giving me a force R, it's getting the same force. Well, they don't cancel each other. So you're really making a conceptual mistake if you do that. And in many books, I've seen it for different classes and courses and different textbooks. Wherever you have to do with action-reaction forces and contact forces, they put you R on both sides. I've seen it before. I don't know why. That is just conceptually wrong. And so if that's the case, then here I have a minus FF, right? I'm just drawing it there because I don't want to pollute this drawing here, but that's what I have. I could redraw this and just do a single particle here with M2, G, minus R this way, and minus F of friction this way. So you start with one block diagram where you're free to draw your reactions and force of friction anywhere you want, in which direction you want, because you don't really know them. But once you don't do this drawing, then you're not as free on the second one. Why? Because now I'm going to do the third one, which is the system. For the system, this is what I get. I get force of gravity, M1 plus M2G, the same reaction from the ground that touches the wedge, that is applied to the wedge, and that's it. Because guess what? I took into account the internal forces the right way, so when you add them together, from the system's perspective, they are canceling each other, which is exactly what I assumed when I derived my F equal ma of the center of mass. So if you don't do this right, this is a big conceptual mistake, because they will not cancel here. You will get a 2R and 2 force of friction. So you're basically saying that you put two objects in contact with each other and they're going to fly away. That's what you say, basically. If you have R and R, you're going to have 2R here, and this thing is going to just fly away for no reason. That would be cool. We'll save a lot of money, right? But it doesn't happen. Okay. So these are the three free body diagrams. Now I can start writing some equations of motion. I have no idea when we're supposed to stop here. What time? 40, thanks. Probably shouldn't erase these. Okay, let's start writing these forces here. See what we get. So N is going to be some NEY, right? Good. Then, of course, M1G is going to be minus M1G EY. I'm just writing each single force. Then I have M2G, which is going to be, once I express it in the coordinates, in one of the coordinate systems I defined, is minus M2G EY. This is probably overdoing it, but you know, better be safe than sorry. I'm going to write all of them. Okay. Then we have the reaction, R. I really don't have space here. R. This is R. What did I call that? Little EY. So that's why I really wanted to use another reference frame. It just makes it easier. Otherwise, you have to have that cosines and sines of beta. Not a big deal. What else is left here? Nothing else other than the force of friction, right? So the force of friction is minus C VREL. So now we have, again, to go back and compute this VREL before we can move on. Yeah, I can probably erase this at this point. What is VREL? You know, I erased it, but I want to redraw it down here just to take a little less space. Okay. It's always the same story. You start from definition instead of skipping steps unless you're 100% sure about what you're doing. And I'm not, and so I do it. So I have to compute the velocity. Which one? I started defining F of friction from the wedge point of view. So the force of friction, the way I defined it, F of F, and then I have the minus F of F there, sees the wedge as the particle on which the force is acting. So I want the velocity of the wedge as seen by an observer fixed to the ground minus the velocity of the point of contact, whatever you want to call it, as part of what? The block as seen by an observer fixed to the ground. Does it make sense? The surface of interest now is the block. The block sees this other object moving and is acting on it with that force of friction. Is that making sense? But how about I pick the block as this, because I can do it. This is actually any generic reference frame A. I don't have to do ground. I don't have to do anything that I don't want. I can pick the one that is more convenient. And so if I pick A to be actually B, then I just get the velocity of the wedge in B. So now you're sitting on the block. You're an observer fixed to the block. And you see this thing moving under you. And what is that? Look at this. You're right here. And you're looking down.
Well, it's moving the opposite. It's just going to be negative. The velocity is 1.
Make sense? If x2 is the only coordinate which is giving me the position of the block with respect to the wedge, it's also, you can do it the other way, it's also giving me the position of the wedge with respect to the block, but you just have to change sign, right? It's almost like saying, okay, if I'm sitting with the block, I'm deciding that this is my origin, and my new x, x3, is equal to minus x2. You're defining yet another coordinate, right? That's pretty much what we're doing here. Okay, that's my relative velocity. So my force of friction is minus, well, minus and minus goes away. So it's a cx2 dot ex, little ex. Okay, cool, I have everything. Is this clear? Do you want me to spend a little more time on this? No? Remember, whenever you talk about reference frames, you really need to make the effort in your mind of actually sitting in the reference frame and see what's happening from that perspective. Okay. Okay. So let's write the Newton's second law for the wedge. How about that? So for the wedge, I have m1, acceleration of the wedge, x1 double dot ex. This is equal to n ey. I'm looking at these forces here acting on the wedge. Minus m1 g ey. And then I have plus r little ey. And I really don't want to go on the next line here. And then what else is left? Force of friction plus cx2 dot ex. Missing anything? Doesn't look like. The block m2 x2 double dot. Oh, I'm sorry, I don't know what I'm doing here. I'm not even looking. Okay. x1 double dot ex plus x2 double dot little ex. Doesn't matter for now, they're different coordinate systems, it's okay. Okay, here I have, let's see, m2 minus r, yeah, minus m2 g ey. Then I have minus r ey. And then I have minus cx2 dot ex. Now we think about this. Do I have enough? Can I find my differential equations of motion here? What do you think? The unknowns are really n and r, right? Those are the two things that are bothering me a lot. And I'm telling you, I don't think you can go through these. There is nothing you can do, scalar products, manipulate these things as much as you want. You're not going to be able to remove them from there. Why? I mean, we can try playing with it, but I'm telling you that the reason is that these equations are not independent. How can they be independent? Look at these two forces. Those two are connecting them. I'm not going to be able to completely eliminate r and n from just these two. You can try. Actually, I invite you to do it. We probably don't have time. I really want to finish this. But you can try as much as you want. Conceptually speaking, when you have a system of particles and you do the free body diagram of each single individual particle, those are not going to be sufficient. You need to do something that combines them. And that's my last one. For the system, I know the following. I know that summation F, all external forces, is equal to total mass, acceleration of the center of mass. What is F? F is only n plus m1 plus m2 g, right? That's all I see from that free body diagram. And this is equal to, what is the acceleration of center of mass now? How did we define it? It's the, well, there is, this m will simplify, right? So I basically will have m1 acceleration of the wedge in g plus m2 acceleration of the block in g, right? Make sense? Remember the definition? And so this is m1 x1 double dot ex plus m2, that expression there, x1 double dot big Ex plus x2 double dot little ex. Now with this equation and one of those two, I invite you to try and do it. You should be able to get to differential equations of motion where you don't have to deal with these unknown forces, the reaction between the two objects and the reaction from the ground on the wedge. So the line of thinking is the following. If you have a system of particles, when you get to kinetics, the single individual body diagrams are not sufficient by themselves because they're all connected to each other. This is touching this body, so there is a connection here with the internal forces. If there was a third one, it would be the same. I'll never give you more than two probably in a problem, but because it gets really big. You really have to handle a lot of free body diagrams. If you have three particles, I don't know how many you get. You have three, particle 1, 2, and 3, and then particle 1 and 2, particle 1 and 3, particle 2 and 3, and the whole system. You get 7 body diagrams when you start pairing all these different combinations in principle. So we'll never do that. But this is the take-home lesson is if you stick with the individual body diagrams, you're not going to be able to solve the problem because there is more than one particle. They are exchanging internal forces, so you need to have something that puts them together, in this case the system of particles body diagram. I really invite you to go through these and try to see how you can manipulate and actually get rid of R and N and solve it. And you let me know if you have any issues. But this is why finding this expression is extremely useful, because go back to what we've done. We removed from the equation all these internal forces. Whatever they exchange with each other, that doesn't go here. So it gives you the behavior of the system as a whole from outside, not caring about internal forces. And that gives you the additional equation that you need to actually solve the problem. Try it. Please try it. Try to do it from just these two. See if you get anything out of it, and then see what is the advantage of having a third equation. Okay? We'll start angular momentum next time, which is Monday. There's no lesson on Friday. Thanks.